Section 10.2, plane curves and parametric equations. In algebra, equations are graphed in two variables, x and y. By introducing a third variable, t or theta, called a parameter, you can now see when an object was at a specific point as it travels along a path defined by a function of x. By writing both x and y as functions of t, you obtain parametric equations. The path the object follows is called a plane curve. This curve is still graphed in the xy plane, and each set of coordinates is determined from a value chosen for the parameter t, and the points are plotted in the order of increasing values of t. This is called the orientation of the curve. Examples. So let's sketch the curve and eliminate the parameter, indicate the direction of your graph, then check it on the graphing calculator. You will notice that both x and y are functions of t. And I want t to go from -2 to 3. What does that mean we're going to do? Substitute -2 into x and -2 into y and get my point. Substitute. Let's just increase by units of 1. So t equals -2, t equals -1, substituting into both, t equals 0, and so forth. If I sketch the graph of this, we can see that at t equals 2, my point is 0, -1. That would be right here at t equals 2. At t equals -1, that will give me the point -3, -1/2. At t equals -4, I'm at 0. At t equals 1, I'm at -3, 1/2. At t equals 2, I'm at 0, 1. And at t equals 3, I'm at 5, 3/2. And you can see that the arrow is telling you the direction we are going. Now, let's eliminate the parameter. Now, in our review of conic sections, you can see this appears to be a parabola. And it is a parabola where I have two y's for each x, so the y is going to be squared. When this gets done, I should have an equation in x and y where the y is squared, the x is not, and since we're opening in a positive direction, my coefficient would be positive. So how do I eliminate the parameter? It's real easy. I'm going to take this equation, t over 2, and substitute it, solving for t, substitute that into my x equation. And notice that we get y squared minus 1, so my y is squared. My coefficient is positive, opening in the positive direction. Now, for AP exam, if you are asked to sketch a curve using parametrics, do not draw the arrows unless you're asked for the direction. Otherwise, don't do it. Okay, pause the video and write down this explanation. I want to look at how this looks on the calculator. So on the calculator, we are going to do a couple of things. So the first thing we want to do is get our calculator in parametric mode. So go to mode and get it in the parametric version. Okay. And we're going to go to y equals. You'll notice that our display has changed. Now it says xt1, yt1. X as a function of t, y as a function of t. This is graph number 1. So go ahead and enter this in on your calculator. T squared minus 4, and again, you have a t button, which is nice. You don't get to use that very often. And t over 2. Okay. Now, we're going to go to the window. Here, it asks for my t value. So my t in this problem is between -2 and 3. So I'm going to do that. Now, I'm going to start with a large t step. This means it's going to evaluate it every 1 unit. So like our chart, we increased by 1. I'm going to show you what happens with that. And I want to figure out what my window needs to be. If t is -2, substituting that into here, -2 squared is 4, minus 4 is 0. But I need to know when y is 0, and I need to know how far we're going to go. Well, when t is 0, my x is -4. So the farthest left I'm going to be is -4, right? So I'm going to go to -5. So I'm going to let my x minimum be -5, max be 8. My scale is 1 unit. I'm going to let my y minimum be -3 and max be 3. Now watch the graph. I'm going to go to my y equals, and I'm going to turn these two equations on. I had already entered them. Got to have them on. Also, what I'm going to do is I'm going to go up here and I'm going to second F6, make sure I'm in the path mode. When you have it in path mode, it's going to show you the little bouncing ball as the path of the graph occurs. And here we go. Watch fast. Woo, that happened fast. Okay, I'm going to regraph it. That happened really fast. You can't even see the bouncing ball. In fact, you'll notice this doesn't look very smooth. That's because my t-step is too large. I need to make a smaller t-step. Maybe I'll go 0.5. It's going to calculate values for my graph every 1/2 unit. Now let's go back and see what happens in the graph. It's a little bit slower. You got to see the ball one more time. But you know, I can get an even better graph, maybe by 0.1. Now watch. And notice, look at that. It's slowing down there. It's speeding up a little bit there. That would be interesting when it comes to velocity, wouldn't it? Okay, and if I really wanted to really get a good look, maybe 0.01. Now that is going to calculate a value every 1/100th. Now you can see that is maybe slower than we want it to go, right? So if you're graphing something and you want to stop the graph, hit the on button, it completely breaks the graph. If you hit the enter button, it pauses it. But if you hit the on button, it stops it. I'm going to go back to my window and maybe I'm going to change it to 0.05. Okay? And now let's see what happens. That's nice, right there. 0.05 is giving me a good slowing down as it makes that curve. There we go. Okay, but in most cases, 0.1 is going to work just fine. Now, if we put it in dot mode, go back to my y equals, and let's change it to dot. Watch what happens when I do it in dot mode. In dot mode, you can see how often it's being calculated, and you can see that it's much more dense here because, of course, my coordinate points are closer together. Very nice. Now, to eliminate the parameter, let us remember, eliminating the parameter means solving one of the two equations for t and substituting it into the other equation. Okay, let's look at example number 2. For eliminating the parameter, we have to decide which one is going to be easier to solve for t. Look where your t is here. Even if I did the reciprocal of my equation and got t plus 1 over t equals 1 over y, I would have this to be 1 plus 1 over t. I am still going to have quite a bit of work to solve this for t. So maybe what I want to do is take my x, square it, which gives us this, and it's going to be easier to get an equation for t in terms of x. Now, let's look at y. Y is t over t plus 1. T over t plus 1. So I could get a common denominator, combine similar terms in that denominator, and notice that I have 1 minus x squared over 1 over x squared. The x squareds cancel, and I get y to be 1 minus x squared. But there's another way we could have thought about this. We could have, from this point, made this 1 over x squared minus x squared over x squared, and we can very quickly, in one step, get here. And now we can look at our graph. Again, we're not given what values for t, so if I just let t equal 0, when I substitute t equals 0 into x, I get 1 over the square root of 1. So this is 1. And for y, when t is 0, I get 0. So there's my first point. When t is 1, I get, for x, 1 over square root of 2. For y, I get 1 over 1 plus 1. So I get the point when t is 1, 1 over square root of 2, 1/2. That's right here. Okay, pause the video and write down this explanation. Okay, so we have this graph here, and we can graph this by hand, but let's see something interesting. When t is 0, substituting 0 into t, I get for x 1, and for y, I get 0. When t is 1, I get for x 1 over the square root of 2, and for y, I get 1/2. When am I going to get 1 for y? When am I going to get 0 for x? I'm never going to get 0 for x because my numerator of my fraction is 1. This is never going to be 0. It's going to get very close to 0. When am I going to get 1 for y? I'm never going to get 1 for y. It's going to get very close to 1, but it's going to be a little less than 1. And we can test this theory. If I go to my window and I just say, all right, let's just go from 0 to 10 and try that. And I'm going to have my t-step in 1 unit so it'll graph fast. Look, it doesn't get all the way to x equals 0 or y equals 1. So let's say, well, maybe let's take it, let my t-max be 100. Okay, I'm getting closer. Let's let my t-max be 1,000. You can see it's getting closer, but it doesn't ever actually get there. Now, is the graph what we expected? Sure. A parabola opening downward, y-intercept 1. And you can see that if you keep letting it graph, it's eventually going to get closer and closer, and it's going to look like it gets to x equals 0, y equals 1, but we know it's going to get very close to it, not exactly there. And we can zoom in on that spot, and it'll be a limitation of the calculator that it shows you that it's getting to the point 0, 1 on the xy coordinate plane, but we know better. Okay, let's look at the equations. X equals 3 cosine theta, y equals 4 sine theta, where theta is from 0 to 2 pi. Well, we know we can calculate those values very nicely. We know that at 2 pi, we're back at where we were at 0. And let's eliminate the parameter. If x is 3 cosine theta, x over 3 is cosine of theta, y over 4 is sine of theta, and we know that cosine squared theta plus sine squared theta is 1, and we get that. Ooh, what is that an equation of? It is a vertical ellipse centered at the origin. We know it's vertical because my a squared is larger than my b squared, and it's under the y squared term. So we have an idea of what this looks like. We can sketch the graph. At theta equals 0, which is out here, I'm at 3, 0. At theta equals pi over 4, I'm at 3 square roots of 2 over 2. Square root of 2 is about 1.4, so 3 times 1.4 over 2 puts me about right there. At pi over 2, I'm at 0, 4. At pi, I'm at negative 3, 0. At 3 pi over 2, I'm at 0, negative 4, and back at 3, 0 when I hit 2 pi. Now, let's look at how this is going to get graphed. Right? I'm going to go to my equations. I've already entered it. Make sure you are in radian mode. And I'm going to go to my window. Now, I certainly don't want what I ended with in the last example. I want to go from 0 to 2 pi. We can enter 2 pi. You have a pi button, use it. My t-step. Rather than just putting a decimal in there, let's look at, why not, pi divide by, why don't we go in increments of pi over 6? Okay. And we already know from what we figured out that our x minimum needs to be negative 3. So I'm going to go from negative 4 to 4. Actually, I'm going to go bigger than that so that this is really going to look like an ellipse. Your screen is 2 to 1, so I'm going to go negative 10 to 10. X scale is going to be 1. Because my y minimum, I'm going to make negative 5 to 5. All right, and now we're ready to watch the graph. Here we go. Oh, I have my t-step too big. Let's go back to my y equals. I need that to be like pi. It was pi over 6, so let's make it pi divide by 24. Still a little fast, but there's a nice pretty ellipse, okay? So I might go and make it pi divided by 36 maybe. Pi divided by 36. And that looks a little bit better. And we can see that we can slow that graph down. Okay, and I'm going to also go back to my y equals. You know what I didn't do? I did not put this in dot mode. Let's go and put it in dot mode. We can see it develop better. Very nice. Okay. Okay. Okay, pause the video and write down this explanation. Number 4. X equals 3 plus 4 cosine theta. Y equals negative 2 plus 3 sine theta. Again, going to get cosine theta equals x minus 3 over 4. Sine theta equals y plus 2 over 3. We're going to work on eliminating the parameter. I get cosine theta to be x minus 3 over 4, sine theta to be y plus 2 over 3. Setting that into our equation of cosine squared plus sine squared is 1. I have a horizontal ellipse centered at 3, negative 2. Why do I know it's horizontal? Because a squared, which is always bigger than b squared, is 16, and it's under the x. So it's going to open horizontally, and you can sketch it yourself. Okay, pause the video and write down this explanation. So I have x equals natural log of 2t and y equals t squared. So how am I going to eliminate that parameter? Well, we know that ln gives us log base e. So log base e of 2t, log is exponent, x is my exponent on e, and it's equal to 2t, and we can easily solve that for t in terms of x. Now we're going to substitute that into my y equals, and here is my equation with the parameter eliminated. Well, what do we know about that? We know what e to the x looks like. E to the 2x means we're going to increase more rapidly, but that 1/4 is going to take 1/4 of the y values, and there it is. Okay, pause the video and write down this explanation. And your TPs for section 2.2 are numbers 3 and 9.